Swayam Prabha. Digital India. Educated India.
In the last lecture, we discussed various recombination and generation processes in a semiconductor, and we also saw how generation processes are basically dependent on the electronic structure of the material. And in this lecture, we will discuss electronic structure of different materials, and if we want, how to change it. So, this is a more material specific lecture, and we can discuss various topics in this lecture, basically related to materials choice. And based on our last lecture, we know that any semiconductor can be used for devices which require light absorption, except that the structure of the device may be affected, whether it is a direct band gap or indirect band gap. But when we are looking for light emission, it is extremely important to know which semiconductor to use, because the light emission that we saw last time is at the band gap energy. So, if I have a material which has a band gap energy equivalent to the red light, then I will get only red emission. Hence, it is important to know how to choose my material or engineer my material, so that I can get different light emission from the material. So, today's lecture will cover basically materials choice, discussion on electronic structure of various materials. We will further have discussion on how to change the band gap. And one technique in this is to change the composition of 3-5 materials. So, composition is one way of changing band gap. The other one would be through strain or lattice mismatching. Yet another technique that is available to us for changing band gap is quantum well structure. To start our discussion, we will talk about 3-5 semiconductors. So, if we want to make a light emitting device, of course, the material of our choice is a direct band gap semiconductor. And 3-5 semiconductors are the ideal system for this material. Now, before I continue our discussion, I would like to make sure we are on the same page. So, if I am looking to make an optical device, obviously I am talking about only visible light, because our eyes are only sensitive to the visible light, and we are talking about visible light, which is basically going from red to blue, and the energy range in which we are talking about if we go from 0 to band gap of something like 7 eV, the visible range So, this is the band gap of the material, this is given in electron volts. The range of energy that we are talking about is, which comes in the visible range, is going to be from about above 1.5 eV to about 3.4 eV. So, this here is about red color, then we have yellow, then we have green, blue and violet. So, basically what this means is that if I want to make a light emitting diode which is emitting in the red, then I need to have a semiconductor which has band gap in this range. Similarly, for the other colors, if I want to make a diode which is yellow, then I must have band gap in the yellow range and so on and so forth. If we look at the 3-5 semiconductors, they are extremely interesting system, and if I plot their structure as a function of chemical bond length, which is given in angstrom. So, the chemical bond length goes all the way from 1.6 to 2.6 for these systems, and we have basically 3-5 which are arsenic based. So, gallium arsenide. In the fifth group we have option of phosphor, arsenide and nitride. In the third group we have the option of gallium, aluminum and indium. So, we can do the mixing and matching in any of these combinations, and that gives us the 3-5 system. So, in this 3-5 system, the first system which was used for making LED was gallium arsenide, and if we look at the gallium arsenide, gallium arsenide has the D value closer to this, and it gives emission in red or yellow, gallium arsenide, aluminum arsenide. It is a very interesting system. If one looks at it all the way going from gallium arsenide to aluminum arsenide, although we are changing the aluminum to gallium atom, the lattice parameter of this particular material does not change, and this is a very good thing for device point of view, which means I can always make make a combination and make a material which is going to be gallium aluminum arsenide in a certain composition when gallium is X and aluminum is 1 minus X. So, I can go from all composition from gallium arsenide to aluminum arsenide, and X will change. Over here X is 100% and here it is 0%, and by changing this composition I change the emission from this material all the way from being infrared to red region. So, it is a wonderful material for that, and for lattice matching it has a very good lattice matching. As we will see later, the lattice matching is going to be important for the material. It can change the band gap of the material if the material is not lattice matched. Let us look at the phosphide systems. The phosphide systems are slightly higher. Here you have aluminum phosphide, it comes somewhere close to the green range, and we have indium phosphide, and gallium phosphide. So, if I try to cover this triangle, what I have is, once again the lattice parameter here is changing between 2.3 to 2.5, but the color that you can get from this system is all the way from blue to red. The another interesting thing about the 3,5 compound is that they have complete solid solubility in each other, which means I can change, as I was describing in case of gallium arsenide, I can change the composition of gallium atom all the way from 0 to 100% and get a new material and a new color, and 3,5 system have this flexibility. In the case of phosphide, we are able to get colors up to green and all the and red in gallium phosphide systems. The nitride systems are a bit difficult because they are of higher energy. Indium nitride is somewhere here, and gallium nitride is above 3.4, aluminum nitride is even higher than 5, around 6. So, this triangle is for nitride system, again in the 3,5 system, this is indium nitride. But as you can see, the nitride systems are take care of the visible light in the upper lower higher energy or lower wavelength. So, if we want to make blue LEDs, you would like to go with the 3 nitride systems, but the problem with nitride system is obvious that there is a huge change in the lattice parameter, and that creates problems in making good materials because of the strain that comes in. But this signifies the beauty of the 3,5 system, which have complete solubility. And hence they allow you to change composition, and which changes the band gap of the material, in turn that you can get different color devices. Now, although we talked about changing the band gap of the material, it is not always necessary that the 3,5 semiconductor is direct band gap for all its composition. Gallium arsenide definitely is direct band gap, and the reason for that is that for different composition material may be different. For example, in the case of gallium arsenide, if you look at the electronic structure of gallium arsenide, the and look at the reciprocal high symmetry points, which are the tau and the chi, then what we find is that for the valence band maxima, it occurs at the tau point, that is the valence band maxima. In the gallium arsenide, which is the direct band gap semiconductor, the conduction band minima also occurs at the tau point. This is the conduction band minima, and as we discussed, then this is a direct band gap semiconductor because the minimum of the conduction band and the maximum of the valence band align, and hence you have a very good probability for radiative emission, and this is a wonderful material for light emitting devices. But we also have another minima at x point, which is also in conduction band. This is another conduction band minima, and in some materials which are variant of gallium arsenide, this minima takes over and the material becomes indirect. So, if we look at gallium phosphide, this is an indirect band gap material, and basically it has similar band structure. The only thing is that now with change in the from arsenic to phosphorus, what we find is that the x conduction band minima is the lower value, while the maxima remains at tau. So, basically what we have is a situation where we have the minima of the conduction band and the maxima of the valence band do not meet at the same crystal momentum value, and this is then becomes indirect band gap semiconductor. but there are certain exceptions. Some indirect band gap semiconductors which are not good for general light emission can emit light through a RG process. We will see an example. They can give radiative emission through a RG center. So, in general it is not good to have RG center recombination since it is non-radiative in nature, but in case of indirect semiconductors it can help and can give sometimes radiative emission. Then let us look at another way of trying to recombine RG centers, and this is an example of the indirect semiconductor in which this electron is not able to recombine with the electron here for the reason because the crystal momentum is very different, and in order to compensate that, as we saw earlier, you need to have a interaction with the phonon. But if we have a RG center which is at some level ET, then this electron can easily interact with the RG center and give you emission that would be in radiative. And this is the case in case of an example is gallium phosphide material, where oxygen and nitrogen impurities, the RG center they create can be used for changing a indirect semiconductor to a radiative semiconductor through this RG center. So, RG centers in general are bad, but sometimes they can be useful. Composition of gallium arsenide 0.5 and phosphide 0.5, which is in between the two composition for arsenic and phosphor. At that point there is a crossover, it stays direct all the way up to about 0.5, and then it becomes an indirect band gap. At the point of the crossover, we basically have a situation where you have the maximum of the valence band and the minimum of the conduction band. So, at this point the conduction band minima are same for both tau and x point, and below this composition the material is direct band gap, and above this composition the material is indirect band gap. And as we have seen through some recombination process, we can sometimes even use the indirect band gap semiconductor to get the light. So, this is one way of trying to change the emission. One way of changing band gap is the composition, and 3,5 semiconductors are wonderful to allow this because they have complete solid solubility in each other. So, you can change composition and go from all the way to 100% gallium to 100% indium on 100% aluminum and change the band gap and as well as the lattice parameter. Now, what are the other ways in which we can change the band gap, and the very important way that works is the lattice matching problem, lattice matching or strain. Now, as we have seen in earlier lectures that the lattice structure of the material is important to decide what would be the electronic structure. So, if I have a way or means by which I can change the lattice parameters, which means that I can change its electronic structure as well, and this also has implications toward how I process my semiconductor, because when these semiconductor materials are deposited, they are actually deposited by using some thin film technology, thin film deposition technology, in which I do epitaxy of the semiconducting material on a substrate. Epitaxy basically means growth of a single crystal on a substrate. In this process, depending on how my material is going to lattice match with the substrate, my material may have a different structure. It introduces strains in the material. So, in this process, if I assume that the semiconducting material which I am depositing has a lattice structure and I am drawing only a 2-dimensional lattice here, this is a semiconducting material which I am going to use for emission, and this is the active material, and then I have a substrate which has a lattice parameter which is slightly larger than the semiconductor. Now, the lattice parameter for the material, let us say this is the film that I have is AF and this is a substrate which is AS. When I try to deposit this material on top of my substrate, the atoms where they are going to match with the substrate are at a different length. As a result, what happens is when I deposit this material, I have two options. One is that the material joins without any change, and if that happens, I will have a structure and my film has to go on top of this substrate, and it would try to take the shape of the substrate. So, this is a new parameter in which I have deposited my semiconductor on the substrate. Now, AF is not the same as AF prime is not the same as AF, and which basically means that I have changed the structure of my material. If I change the structure, it is obvious that the band gap will change. And hence the emission will be modified. So, one way of changing the band structure or the band gap of the semiconductor is also to strain the material, and the way that we process our semiconductor, it can develop into structures which are not its equilibrium structure, which are slightly strained. This particular film is under tensile stress, and because of that a new structure is developed which is also referred as pseudomorphs. This is a pseudomorph and it has a new band gap, and by this technique we can change what kind of emission we are getting from our material. The other side of this process is that I am going to have a substrate but the material that is deposited on it does not change its original crystal structure. In other words, there is no matching of the atomic rows in this structure, and in this case it normally ends up giving you defects like dislocations. This kind of interface which is created between the semiconductor and the substrate is called an incoherent interface. And the earlier is called the coherent interface. Between incoherent interface, this would happen only when the lattice mismatching is high. And the coherent interface requires good lattice matching. So, this is another way of creating strained material. By that we create pseudomers which have different electronic structure and which have different band gap and will emit different light, and that is one way of changing doing the band gap engineering. The next technique that is used to change the electronic structure of the material is quantum wells. Quantum wells is again another technique which is possible because of thin film processing. It is possible for us to sandwich one material between two different kind of materials of a different band gap, and that allows us to create structures which will have a completely different electronic structure. So, what we are talking about here is we have a material which is going to be large band gap, and then we make another material which is going to be low band gap. So, we are using the picture of the band gap structure, where large band gap material is sandwiching a low band gap material. Now, the emission properties of this particular material is going to be just like the bulk material as long as this thickness is large, but as we reduce this thickness in the range of nanometers, the property of this particular material becomes completely different. Now, we have a situation in which in the x direction the electron is confined in a well, but in the y and z direction it is free to move. As a result, that the y and z direction electronic structure does not change, but in the x direction the electronic structure will get quantized, and it will introduce electronic states which are quantized in the x direction, and that changes the emission of the light. The quantum structure gets the quantum emission from quantum well is superimposed on emission of the bulk material. So far what we have discussed is that we can change the band gap of the material. Band gap of a semiconductor can be changed using different means. Via changing its composition, and 3-5 semiconductors provide the entire composition range for this. We can change its structure by straining the material, and this is possible in lattice mismatch with the substrate. Finally, we can create quantum well structures and modify the electronic structure of the material. If you look at materials for devices which require absorption of light, then things are completely different. For example, we are talking about solar cells or photodetectors. Here our aim is different. For example, in case of solar cell, we have a spectrum of solar spectrum which is a very broad spectrum, all the way from infrared to UV. In order to absorb all this light, if we plot intensity versus wavelength, and this is the spectrum of the light coming in, and the device and the material that we have of some thickness x. The material is going to absorb this light only to the extent that for the light for which its Eg is higher. So, the light which is going to be the solar light which will be absorbed by this material is going to be only the amount which is higher than the band gap of the semiconductor. So, Eg is the band gap of the semiconductor. Now, this is the problem here. What we have is a situation where this amount of light is not absorbed, and this is wasted. So, the choice here is to choose materials which will absorb infrared, visible as well as light which might be hitting in the UV region, and hence we need to use materials which are going to have band gaps, need combination of materials to absorb in infrared also. With the blue light also there is a problem. The problem occurs because the amount of absorption in this slab, as discussed earlier, is basically decided by the exponential, and as we go towards higher energy, then the most of the light gets absorbed in the near the surface, because the absorption coefficients are high, it gets absorbed near the surface. The light which is of lower energy continues to go deeper in the material. So, the blue light gets absorbed at the surface and the red light gets absorbed deeper in the bulk. As a result, what we want is we want a material which is absorbing in the blue at the in front of the device. So, this should be a blue absorbing material. Then something in between, and so the first layer should be Eg in blue, the second layer the Eg should be in green, and the third layer should be more red. This way we absorb most portion of the solar cell. Now, what would be the choice of materials in this case? The choice here is mostly not dictated by the band gap, it is more of a market choice. Although silicon in the terms of this absorption does not absorb most of the solar light, but it is a easily and least costly material to make solar cell with, and that is why people use silicon. But if we take some 3-5 compounds and make a triple junction solar cell in which we use 3 different materials, we will be able to capture most of the solar light in this device, and that will give us better efficiency. Similar thing is going to be true for photodetectors. For photodetectors, the application is basically to detect a particular light. And whichever wavelength we want to detect, that wavelength should have, for detection, there should be equivalent to the Eg of the semiconductor. So, once again the problem is of materials choice. So, if I want to detect infrared, silicon is not the choice material, I will go for chalcogenides like mercury, cadmium, telluride. If I want to detect visible light which is higher than 1.1 eV, then I can go for silicon detectors. Now, for the case of detectors, again availability of the current after the light is absorbed in the material depends on whether it is direct band gap or indirect band gap. And this will basically decide the sensitivity of the device. And in order to improve the sensitivity, earlier the same bulk material that we had, we used to use that for making the devices, but now it is possible to change the material absorption properties. We can modify the absorption of a bulk material and that could be done by adding nanoparticles. So far we have discussed various ways of modifying the electronic structure of the semiconductor, which can modify our properties, and for different devices we can get different specifications required. Only thing in this discussion we have only focused on the optical properties, and when we want a device to work, the electrical properties are also important. Hence, there is a optimization, because when we use all these modification, normally the electrical properties take a hit, and in order to make good devices we need to optimize both of them. Earlier we discussed the requirement for light emitting diodes, and we talked about the band gap engineering, and later we looked at how addition of nanoparticles can change the absorption behavior of materials. But point to remember here is that while we are focusing on the optical properties, electrical properties often deteriorate when we do band gap engineering, and hence there is a optimum that needs to be obtained in order to change the electronic structure of the device without changing its electrical properties and modifying its optical properties. So, optical properties and electrical properties are often against each other. You can have a improved absorption, but then it gives you very poor mobility of the carriers, and hence the device will not work very well. So, these two properties have to be optimized in order to get a good device. At the end of this lecture, I would like to look at various materials and their band gaps, and their electronic structures has been discussed. So, if we take group 4 semiconductors, the most common were germanium, silicon. Then we have group 2,6 semiconductor, in which we have zinc sulphide, zinc selenide, cadmium sulphide, cadmium selenide. These are good materials for solar cells, photodetectors. One also uses strain layer silicon germanium to change to have change in band gap. The 2,6 semiconductors or other chalcogenides are also good materials for solar cells. Then we have group 3,5 materials, which are basically gallium, aluminum, indium, arsenic, phosphide, nitrogen. Combination of these material and the entire composition range. These are good material for light emission. And light emitting diodes and lasers. The choice for material is dictated by its electronic structure. The band gap Vg, which is basically the difference between the conduction band and the valence band, conduction band maxima and the valence band minima. The choice of material is also dictated by how electrical properties are dependent, the mobility, and most important that becomes for various devices its availability. And this is the reason for the popularity of silicon. Although silicon is being indirect band gap, it is still more popular for many applications because the availability of silicon, it is cheaper to obtain and use as well. With this, I would like to summarize what we have covered in this lecture. We have looked at materials choice for various devices. We have looked at ways of modifying electronic structure. And ways of changing absorption properties.